Rolling. So now we're going to be talking about specialty engineering, which is unlike the other systems. It accounts for survivability, risk, and reliability. I will be talking about survivability for the next couple of minutes. Next slide, please. And this is me. Okay. All right. So the requirements that we derived from the survivability team was that the spacecraft had to essentially survive the harshness of the space environment. And seeing that the mission is very long, we would need to consider this in great detail. So the environments we considered were micrometeorite, orbital debris, radiation, vacuum, and plasma. And for the sake of saying it ahead of time, we really focus on the micrometeorite and the radiation and the grounding. The other ones, we kind of considered it as, okay, what do we need to do to avoid issues in this area? Next slide, please. So here's some examples of environmental hazards, which I'm sure you are familiar with. We'll be doing a double Earth flyby. We'll be doing a double Earth flyby in slightly above Leo. And knowing that we have a fairly large debris ring there, we needed to do analysis to see the probability of a piece of debris or micrometeorite actually impacting our spacecraft. The next one is that Uranus is actually a ring system. And so because of that, when designing our trajectory, we actually decided that we would not risk going through the ring plane, similar to what the Cassini mission did. Also, we need to consider arcing. Obviously, usually spacecraft feel different voltage differentials throughout, and so we needed to properly ground all of this. Also, radiation, which is probably the most notorious of all. We will be doing a flyby of Jupiter, so we also needed to consider what this would do to our electronics.
If you're orbiting Uranus, how do you
So essentially, we have a highly elliptical orbits.
At Uranus, our periaps is just outside the outermost ring, so our lowest altitude is actually above the ring, so we avoid them entirely.
And you're confident enough that you know where the outermost ring is?
Yes, there's the most visible ring that extends to 103,000 kilometers.
That's the dust ring.
That's the dust ring. There's actually the outermost ring, and then there's a dust cloud.
There's solid rings, and then there's dust regions inside and outside. And since the region is fairly unknown, the only information that we had was from Voyager, as well as Hubble's observations in 2007. So from that information, that's why we decided to clearly avoid the area.
But I mean, I understand it, but isn't there a chance that you're wrong and you get there and there's stuff further out than you think?
We've also, I mean, it's possible, and because of that, we tacked on an extra 5,000 kilometers to our periaps altitude, which hopefully will account for any uncertainties in the ring size.
That is a good point. Next slide, please. Okay, so for micrometeorite orbital debris environment, which I'll call MMOD, the first step was to characterize the fluxes. So how much debris is out there, because that affects the probability of being hit. So for fluxes, we use the interplanetary flux model, and for the orbital debris, we use the available orbital debris models currently available. From that, we derive these probabilities, and so for our Uranus operations, since we'll be avoiding the micrometeoroid area, and there'll be fairly sparse amounts of dust where we will be, we calculated a probability of no critical failure as 0.95. For transit, however, because it's a long duration, we had to consider the time. Because of that, our probability came out to 86%. For Earth specifically, it was calculated using solely orbital debris and came out to a 93% for each flyby. With that, it was fairly obvious that protection needed to be implemented. There was no way around it. From that, we decided to use a toughened MLI made of Nextel and Kevlar, approximately 20 layers for each spacecraft. Also, ways that we didn't want to add too much mass for the purposes of shielding. So we really tried to account for this in our layout. And in our layout design, we focused on putting the sensitive instruments as close to the center. For example, the propulsion tanks, the pressurized tank. You don't want something hitting your pressurized tank. I'm sorry. Okay, so then from all of those considerations, we said that our PNCF after mitigation was approximately 99%. Next slide, please. So radiation. So radiation is actually a very hard environment to characterize without the use of models. I do not have this available. However, because of that, we characterized it using heritage machines such as Cassini and New Horizons. New Horizons had a 25 total ionizing dose, which they added a 2 radiation design factor to it, coming out to a 50K rad requirement. From that, their components were derived to be 100K rad for their entire mission. Using this is what we decided to go with. So to get to that, we will be using radiation-hardened components as well as shielding on our electronic boxes and our rad-sensitive components. Next slide, please. So plasma and vacuum environment. So plasma, it causes charging, and we don't want any arcing to our sensitive instruments. Because of that, we will utilize a multi-single point ground. We worked specifically with harnessing and power to determine this was the best method for us. Also, we will use electrical filtering on circuits, and the most important one is that our structure will act as a Faraday cage. Now, however, our structure is made of composite. Because of that, we will need to account for this in wiring, either through aluminum or copper wires. Next, which is usually the most practical, is in integration and test, we will utilize standard ESD procedure. As for outgassing,
wait, so your instruments kind of, does electrical pass through your Faraday cage?
does electrical pass.
You've got instruments that are outside
Correct.
the Faraday cage, basically.
Right.
Which means you've got wires going out. What are you doing about that?
We would be hoping to isolate all of that. We haven't gone into as much detail in terms of specifically if there's that wire, how exactly is it going to be grounded properly. But if we could easily look into that further. So continuing on with the vacuum environment, obviously outgassing is always a concern, so we will make sure that the materials that we have are not near any instruments to cause contamination if they do outgas, as well as beginning of life of our mission utilizing venting techniques. Next slide, please. So now we will get into the risk and reliability, and I will introduce Andrew Bacco.